Our presentation is Composition of Asteroids and Their Formation and Evolution Within the Solar System. I'm Ly-McMurray.
I'm Dhevan Sluiter.
I'm Noah Byars.
I'm Jade Park.
I'm Maia Freeman.
I'm Max Weitzner.
I'm Ly-McMurray.
And I'm Stella Ristic.
And together,
we are Planetary Geology.
The goal of our research is to determine the relationship between the mineralogical composition of various asteroid classifications and their role in the evolution of our solar system. By establishing that connection between asteroid compositions with their significance in our solar system's early history, we can further define and expand the knowledge on the separation of gaseous and terrestrial celestial bodies, the transportation and evolution of life on Earth, and the processes which occur in the formations of new solar systems. Our research can also answer questions about the creation and dispersion of the Milky Way.
To understand asteroid formation, we must first know about the formation of the solar system. The process of star system formation begins when a large dense cloud of molecular gas begins to spin, forming a disk. Materials from this disk are pulled by gravity towards its center, creating enough pressure to fuse hydrogen atoms together into helium. The balancing act of nuclear fusion pushing outwards against the inwards pull of gravity creates a star, such as our Sun. The remnants of the stellar nebula begin to clump together and collide, forming early versions of the planets, moons, and asteroids we see today.
So, what are asteroids? Asteroids are classified as rocky celestial objects that maintain elliptical orbits around our Sun. They are considered to be the material left over after the formation of the Sun and all of the planets in our solar system 4.6 billion years ago. They are also pieces of space debris with insufficient gravity to form planets or moons. They can also be characterized as past celestial bodies that were destroyed by violent collisions occurring in the early stages of the formation of the solar system. The different types of asteroids are differentiated by their spectra, composition, structure, and location in the solar system. The types of asteroids that we chose to focus on for this project are C-type, which represent carbonaceous chondrites, S-type, which represent silicous, M-type, which represent metallic, B-type, which is a subtype of C-type due to the blue spectral slope being different, and V-type, which are basaltic asteroids and are pieces of Vesta that broke off of the main asteroid. The graph included is a representation of the distribution of asteroids in the solar system based on spectral type and orbital resonance. It is shown that the M-type asteroids are exclusively found in the main belt, whereas C-type and S-type are found inside as well as outside of this region.
This leads us to the question of how asteroids form. Rocky asteroids with cores form similarly to the terrestrial planets. During the birth stages of the solar system, when everything was much hotter, spatial bodies were molten, and the denser metals, such as iron, sunk to form a core, and the less dense rock rose to the surface of these objects. These structures that did not form moons and planets are known today as the asteroids. Most asteroids form from the accretion of dust and metallic material left over from the formation of the Sun 4.5 billion years ago. In addition, some asteroids can also break off of other planets and celestial objects, an example of this being the asteroid Bennu. Asteroids can also be the product of large and small-scale impacts between celestial bodies. The image in the bottom right of the slide illustrates two examples of these collisions that spread debris throughout the solar system and form new bodies/asteroids.
Our data was obtained through various scholarly and credible sources such as Google Scholar and EBSCO. We chose to research the different classifications of asteroids, specifically the C, V, B, S, and M types. With this information, we studied the composition, location, and possible origin of the asteroids from these classifications in order to derive a conclusion which answered our initial research question of what does the mineralogical composition of asteroids tell us about their formation and evolution in the solar system.
We researched Vesta due to its unique characteristics. For example, 6% of all main belt asteroids are related to Vesta, granting the asteroid and its relatives their own classification of asteroids, the V-type. Bennu was chosen for the immense amount of data obtained during the OSIRIS-REx mission, including the asteroid's connections to a larger oceanic asteroid and its unique classification as a B-type asteroid as a result of its blue spectral slope. We studied Ceres due to its central role in the Dawn mission and unique core composition, which suggested its dwarf planet status. Itokawa was researched since it is a notable S-type asteroid that had been heavily studied in the Hayabusa mission, and because its small side adds diversity to our sampling. And finally, we chose Psyche because of its exposed nickel-copper composition that mirrored the building blocks of terrestrial planets in our solar system, as well as its relevance to the upcoming Psyche mission.
Our first three asteroids are Ceres, Vesta, and Psyche. Ceres is made up of a water-ice mantle, sodium carbonate, ammonium chloride, organic compounds, and rocks with a composition of C1 chondrites. Vesta is composed of basalt, nickel iron, pyroxenes, and oxide minerals. Vesta and Psyche also both contain silicates, though Psyche's composition is more that of nickel, copper, and iron. Both Ceres and Vesta are around 4.5 billion years old, while the age of Psyche remains unknown. Ceres has a density of around 2,700 kilograms per meter cubed. Vesta has one of 3,456 kilograms per meter cubed, and Psyche's density is around 2,950 kilograms per meter cubed. Finally, both Ceres and Vesta have a homogeneous structure, as well as a core, while Psyche has a uniform composition and a porous surface with numerous craters.
Bennu is composed of various materials, including serpentine, magnesium sodium phosphate, organic compounds, and clay, which were formed 4.5 billion years ago. Bennu has a density of 1,260 kilograms per cubic meter. Itokawa is composed of silicates, water, and organic compounds. Similar to Bennu, Itokawa's rocks were formed 4.562 billion years ago. Itokawa has a higher density of 1,900 kilograms per cubic meter. Many large rocks of similar composition comprise Itokawa, while Bennu has a homogeneous structure with a metallic core.
The arrangement of asteroids is due to the way our solar system formed and the compositions of the asteroids themselves. During the formation, only rocky materials were able to withstand the heat of the sun, while icy materials and less resilient matter settled in the outer regions of the asteroid belt and solar system. This is why metallic and stony asteroids, S and M types, are found closer to the sun, having rockier compositions, while asteroids containing water or ice, such as C, V, and B types, are found farther away. Crystalline silicates are commonly found in C, V, and B types, and they're located at distances where the temperatures are too low for in situ annealing, which is a type of heat treatment used to alter the physical and chemical properties of a material. In other words, they are located too far from the sun for the necessary thermal energy. C, V, and B types asteroids are all composed of silicates, clay, pyroxene, basalt, and magnesium, and therefore tend to be found in the outermost regions of the solar system, located about 3.5 AU from the sun. S-type asteroids are the closest to the sun, only 2.2 AU away, and they're made of stony materials like nickel iron and magnesium silicates. M-types are located in the middle of the asteroid belt, 2.5 to 3.3 AU from the sun, made up of primarily iron-nickel metal. The image on the left portrays the percent populations of C, M, and S-type asteroids and their respective compositions. It most accurately shows the immense population of C-type asteroids compared to S and M types, and the differences in rocky compositions versus organic. The image to the right is a graphical analysis comparing the primary asteroid classifications to their distance from the Sun, showing S types as the closest and C types as the farthest. The image above represents silicate and metallic asteroids and further breaks down their mineralogical compositions into specific elements.
Vesta, a V-type asteroid, is assumed to be formed from dust accretion because of the many simulations of our early solar system's protoplanetary disk. This formation process is also the reasoning behind Vesta's large size, because as it accreted more and more dust, the accretion process accelerated. The group of HED asteroids, Howardites, Eucrites, and Diogenites, are all believed to be pieces broken off of Vesta because of the similarities in their compositions and spectra. This ejection is shown in the middle of the bottom image. Both Howardites and Eucrites are made up of basalts, pyroxenes, and silicates, while Diogenites are just made up of pyroxenes and silicates. These small differences in composition, which you can clearly see in the images on the right, are due to the point in time in which they are ejected from Vesta, because as the core went through differentiation, the minerals on the surface changed. This process is portrayed in the top image.
Psyche is an M-type metallic asteroid composed mostly of nickel-copper alloy, silicates, and iron, and is a planetesimal, or failed planetary core, as most M-type asteroids are believed to be. This indicates that Psyche coalesced from dust and metals that were around during the beginning of the solar system after the formation of the Sun. Metallic asteroids such as Psyche start out fully molten. However, over time, they solidify and form a uniform, solid asteroid. Observing the surface of Psyche shows that it has been impacted various times, making its surface rough and porous. The image on the right of the slide shows a nickel-copper alloy, the very substance that makes up 60% of Psyche, and the image to its left depicts the launching of the Psyche mission in 2023, which will study the asteroid in depth.
Ceres is a C-type asteroid. C-type asteroids are known to be a source of carbonaceous chondrite meteorites, with the carbon composition resulting in a dark charcoal-like color. C-type asteroids have a very low albedo, which means that they don't reflect most of the light shown onto them, making them very hard to view. Most C-type asteroids are at least 3.5 AU from the Sun on the edge of the asteroid belt, being one of the more ancient asteroids of the solar system. These asteroids are the source of carbonaceous chondrite meteorites. Most C-type asteroids haven't reached above 50 degrees Celsius and are believed to be composed of around 22% water. Ceres itself is theorized to have formed from silicate rocks and silicate organic matter accumulated on celestial bodies with the surface water near Jupiter and Saturn, while also being formed of clay and dust. Ceres tried pulling all of these particles together to form its own planet but failed, resulting in it becoming a planetesimal. Some hypothesize that C-type asteroids may have delivered volatiles to the inner solar system, particularly the early Earth.
Bennu, a B-type asteroid, contains many different elements and compounds that are telltale signs of its origins. Magnesium sodium phosphate, found in the samples collected from the OSIRIS-REx mission, suggests that Bennu broke off from a much larger and aqueous, carbon-rich asteroid 700 million to 2 billion years ago due to a collision in the main asteroid belt. The scattered pieces moved in a near-Earth orbit due to gravitational interactions with the gas giants to form Bennu. This debunks common belief, as asteroids are not always monoliths or a singular rock. They can be what astronomers call rubble piles, boulders and debris that have coalesced under the influence of gravity. The current structure and measured bulk density of Bennu tells us that the asteroid is a conglomeration of clay and serpentine. OSIRIS-REx samples also show evidence of organic molecules, such as carbon, oxygen, and nitrogen. This implies the possibility of impacts from asteroids similar in composition to Bennu being the source of organic molecules on Earth, and thus the origins for life on our planet.
Itokawa, similar to Bennu, formed from debris resulting from an impact of another asteroid with Itokawa's parent body. The largest boulder on Itokawa, pictured to my left, is evidence of this formation because it is too large to have been formed by any collision displayed in Itokawa's impact craters. Itokawa's density, which is lower than what would be expected from a solid asteroid of Itokawa's composition, also supports ideas of a parent asteroid. Much of the ejecta from the impact on Itokawa's parent body gravitated towards each other, forming an asteroid, as shown in the diagram below. Itokawa had enough local gravity to agglomerate these rocks, but not enough to consolidate them into a solid asteroid without empty space. This led to the amount of empty space shown in Itokawa's density. Itokawa's low local gravity also accounts for its low base shape, having many lobes around the asteroid, as seen in the final image of the diagram below. Itokawa's parent body was likely a C-type asteroid, as shown in the amount of water and organic compounds found in Itokawa's regolith. However, Itokawa itself is an S-type asteroid because its composition is predominantly silicates, such as olivine and pyroxene. This shows that Itokawa formed from a silicate-rich area of its parent asteroid's crust that underwent metamorphism. Dating of particles returned from Itokawa indicates that this metamorphosis occurred 4.6 billion years ago.
In conclusion, examining the different components of types of asteroids helps to further our understanding of the development of our solar system and potentially the development of life on Earth. The composition of asteroids helps us to understand their relative locations in the solar system. Rocky materials are closer to the Sun due to their tougher materials and composites being able to resist alterations from the intense heat and radiation from the Sun. A key indicator for this is the asteroid belt that divides the rocky planets from the gas giants. This is demonstrated in the image where there is a large population of asteroids in between Mars and Jupiter. Because of the proximity to the Sun, rocky planets formed closer to the Sun, and planets made from gas and ice are further away. This also leads to less resilient carbonaceous chondrite composites.
Psyche is a NASA mission to study the metal-rich asteroid it was named after, which is located in the main asteroid belt between Mars and Jupiter. This is NASA's first mission to study an asteroid that is more metal than rock or ice. Psyche launched on October 13, 2023 from the Kennedy Space Center aboard a SpaceX Falcon Heavy rocket in order to release the satellite. Psyche will orbit its target in 2029 and collect data about the surface, composition, and structure, which will help us understand more about the core of our planet and teach us more about planetary formation and all.
As a successor to the OSIRIS-REx mission, OSIRIS-APEX will reach the S-type asteroid Apophis during Apophis's close encounter with Earth in April of 2029. Our planet's gravitational pull is expected to alter the asteroid's orbit, leading to changes in how fast Apophis spins on its axis and could cause quakes/landslides. APEX will allow scientists to observe these changes and view the composition of material just below the asteroid's surface rather than just the regolith.
One area for possible future work is in the analysis of Kuiper Belt objects. While similar to the asteroid belt in many ways, the Kuiper Belt is much farther away from the Sun, as visualized below. This allows for additional investigation into the links between the locations and compositions of asteroids. Being much larger than the asteroid belt, the Kuiper Belt contains many bodies, such as those pictured around me, which could be the basis for significant research. This research, similar to that which has been conducted on asteroids closer to Earth, would be particularly important to shed light on the formation of trans-Neptunian objects and the ice giants they encircle.
And these are our sources, most of which are images.
The NASA Seas internship offers a wide variety of activities and experiences that expose interns to a vast amount of knowledge and discoveries. A few of the highlights from the program include conducting geology field research, where we embarked on a journey to extract rock samples for analysis, research, and comparison to extraterrestrial samples. The Johnson Space Center visit, in which we traveled to Houston to go on a tram tour of the Center and Sea Rocket Park, the Astronaut Training Facility, and the Mission Control Center. We also enjoyed Six Flags Fiesta Texas, where we had a great time bonding as a team outside an academic setting, and the University of Texas Aerospace Engineering Department, in which we had the opportunity to tour the incredible aerospace facilities at the university. Finally, our trip to iFly, where we learned about wind tunnels and terminal velocity, and got to experience indoor skydiving.
We also had a few challenges with the internship. The first one was planning an experiment for our Z-Cube. This challenged our abilities to brainstorm, test, and narrow down the ideas for our project. This proved especially difficult due to experimental constraints, such as the camera angle, small space, and limited time in microgravity. Through teamwork and help from the amazing SEAS mentors, we were able to design an innovative experiment that will be successful despite these constraints. The second one was performing our planetary geology research, which proved just as rewarding as it was challenging. Every step forced us to stretch our abilities from developing a research question that everyone felt passionate about to analyzing asteroids at deeper and deeper levels to creating this presentation. We have learned various skills that will help us in our later careers.
Reflections. Growing up loving Bill Nye the Science Guy episodes and assembling NASA Lego sets fostered my love for understanding our universe. Thankfully, my experience with NASA Seas has not only nurtured this curiosity, but taught me that I have a future in this field. Whether listening to incredible guest speakers, studying various rock processes with Bev, or scribbling mission patch designs while sleep-deprived, I've enjoyed every step of this journey with my fellow interns. I'll be sure to stay curious and achieve my goal of being an astronaut someday, but until then, thank you, Planetary Geology. Let's keep in touch.
I could have never imagined how much my life was about to change when I opened the NASA Seas exhibits letter. Getting to work with similarly minded people has truly been the highlight of my 2 weeks here, and I hope that my time here will stay in my mind for the rest of my career. The things I have learned here have only further cemented my love for space and science, and this passion will follow me for the rest of my life. My rewarding experiences here will continue to aid me in my journey from Earth to the stars.
My experience here at NASA Seas has been absolutely fantastic. There were still definite challenges, but I was able to get past them with the help of my team. Having the ability to conduct experiments, connect with professionals and experts in the field, and get true experience with research was wonderful. I'm excited to see how this internship will help me with my goal of becoming an astrophysicist.
The NASA Seas program is utterly unique from every other. The people we have had the chance to meet and work with are incredibly inspiring and will forever leave a mark on our careers. The opportunity to meet students from all around the country while also indulging in once-in-a-lifetime experiences, including designing projects to be tested in microgravity and scientific research, has been deeply influential. I am so grateful to have had this opportunity and to meet my amazing team and mentor.
Throughout my time spent at NASA Seas, this internship has been a truly eye-opening experience. As someone who has only considered space a hobby, the idea of pursuing it as a career had never come to mind. After these 2 weeks, however, more than ever can I see myself as someone with a future in space. From our lectures with renowned scientists to our intricately planned experiments, I am so thankful for both my mentors, my fellow peers, and the NASA Seas team for making this once-in-a-lifetime experience truly rewarding.
NASA Seas has been one of the most transformative experiences of my life. From the friends I've made to the lessons and knowledge I've gained, being here surrounded by incredible peers, mentors, and speakers that share my interests in space exploration and aerospace engineering has not only been an eye-opening experience, but has also taught me so much about myself and my future career path. I am so grateful for my time at this internship, and I know that I will carry the knowledge I've learned with me throughout my personal and professional lives. Thank you to my incredible team for making my time here so memorable, and thank you to the mentors and organizers for making this experience possible.
This internship, while a new experience for me, has turned out to be both difficult and enlightening. Learning to collaborate with my team members under the guidance of a wonderful mentor in order to overcome challenges in both our research and experiments during my time at NASA Seas has strengthened my drive towards a future in STEM and my resolve when facing difficulties in the journey towards it.
My journey throughout my NASA Seas internship has been challenging. However, my team has made this experience not only successful, but incredibly enjoyable. I am grateful for this internship, and I'm excited for how it has helped me on the coming steps of my planetary research journey.
Thank you!